Okay, thank you very much. So who has been in the talk yesterday? I'm just wondering how. But, so some have not. So I'll just go over the definitions again of conflict-free coloring and even the motivation quickly. And I want to focus on what we call a least coloring version of that coloring. So this is based on joint work with Panos Chilaris, who is a postdoc of mine in Israel. Okay, so a hypergraph, quickly, is a pair V and E is a collection of some collection of subsets of V. So this is a generalization of a simple graph, where so if all the hyperedges, we call the elements in E hyperedges, the element in E vertices, in V vertices, and if all hyperedges in E have exactly two elements from V, then it's a simple graph. So a proper coloring is a of the hypergraph is a function from the vertices to some finite set. Let's call it 1 to k, the integers 1 to k. And we call this coloring, this function, proper coloring if no hyperedge, see, no hyperedge is monochromatic. You see at least two colors. So you color the vertices and you want each set in your set system, in your hypergraph, to have at least two colors present among the vertices in that hyperedge. And chi of h is the minimum number, the chromatic number of h is the minimum colors needed for such a proper coloring. And a CF coloring is conflict-free coloring is a more restrictive notion, where you not only ask that no hyperedge is monochromatic, but you also ask that, in fact, for every hyperedge you have at least one element whose color appears unique, as you can see here. So the
three E's are distinct elements. The three E's are distinct elements.
Yes, right. Amazing. I haven't noticed that. Yeah. So it's the letter plus the coordinate that makes the. Yeah. Okay. So of course, any conflict-free coloring is also a proper coloring, because if you have a hyperedge and it has some unique color, then obviously there is another color, if there are at least two elements. So, and the CF chromatic number is again the minimum number of colors needed to color that, to CF color that hypergraph. And well, yesterday I focused mainly on geometrically defined graphs, which are, say, Venn diagrams of some shapes, for example. So, for example, look at these four disks, maybe ellipses. So the hypergraph is just so those are the shapes themselves are the vertices of the hypergraph, and the hyperedges are all subsets that you can realize by considering a point, and all shapes that contain this point. So given a point, you take all subset of all shapes containing that point, not some shapes containing that point. You must take all the shapes containing that point, and whatever you can realize like that, those are your collection of subsets. So we can have subset containing only this ellipse, or this ellipse, or this ellipse, or these two guys, these three ellipses, or these two ellipses, and so on. And a conflict-free would mean, a conflict-free coloring would mean assigning colors to the shapes, such that in any given point, right, in any given point, one of the shapes containing that point has a unique color among the shapes containing that point. That's just saying that it's a CF color of the underlying hypergraph. And I presented this motivation, which I like to present, so for those of you who haven't been yesterday, that if you have if you maintain some wireless network where you have antennas that represent those by disk according to the coverage area, and you want to assign frequencies to the antenna in such a way that every client will be served. So a client can be served if he can speak with one of the antennas covering that client. And in order to do that, he has to pick an antenna and has to use the same frequency as this antenna uses, and the antennas were pre-assigned frequencies. And the problem occurs if there are two antennas that were assigned the same frequency and they cover this client, so he might have this mutual interference. But we can resolve that as long as there is one frequency of an antenna covering the client, which is unique. And we wanted to hold in any possible location of the client. And this just means that the assignment of frequency amounts to conflict-free color, the underlying hypergraph induced by those disks representing the antennas. And the goal is to minimize or to find a nice coloring which uses only few colors because the frequency spectrum is limited, and so on. Let me go over a brief history that I haven't had a chance to sort of organize yesterday. So there have been numerous papers by now, all kinds of follow-ups from the original paper, which only sort of investigated the case of hypergraphs induced by disks in the plane, which are sort of interesting already by themselves. So the first result says that if you have n disk, you can always use at most some constant time log n colors for such a coloring, and this bound is best possible. You cannot improve it. So there are examples when you need simple examples where you need at least log n colors. And then it was extended by to some other hypergraphs, still geometric, that for example, to pseudodisks and to axis parallel rectangles. So one more thing that the first result was that you can take sort of the primal or the dual hypergraph where you have points, and you want to color the points in such a way that no matter what disk you take, as long as it intersects the point, there will be one uniquely colored point. So for that you also always need log n upper and lower bound. But then it was extended to the case of axis parallel rectangles, where you replace the term disk with an axis parallel rectangle. By the way, the reason I'm insisting on axis parallel rectangle, not just rectangles, because it's meaningless to talk about arbitrary rectangle, because if you take a set of points in general position, then any two are isolated by some rectangle. It's just a narrow rectangle if they're in general position. So every two form a hyperedge. I mean, it's just a complete graph. So you need every 2 points need to be colored distinctively. So you need n colors, right? But if you talk about axis parallel rectangle, it becomes, as you said yesterday, not geometric but extremely interesting. But still a big open problem to close the gap between the best known upper bound, which was improved recently to something like n to the 0.381, and the best lower bound, which is actually something like log n over log n square, which comes from some random construction. This is a paper by Chen, Janusz Pach, Mario Segedi, and Gabor Tardosh. More versions of this problem were studied. One of them that I should mention, which is interesting, is this is a joint work with Noga alone. So if we want to, let's go back to disks. I claimed, the first result says that if you color disks, if you color a bunch of disks, you always, n disks, you can always do it with log n, with constant time log n colors. And I claim that this is optimally. So there are construction, actually very simple. One can just put the center of even with unidisc, you put the center of the unidisc on a line, and you can see that it's a homework exercise to check that if those are unidiscs close enough, say this is less than half or something like that, then those bunch of disks that would look like that, I don't want to draw it because you see it's going to be messy, but they're going to need at least log n colors. But in this example, there is a point that belongs to many disks. You see? There is a point actually that belongs to all the disks. So one natural question is, what if the set of disks have the property that there is another parameter k, and every point can belong to at most k disks? So we conjectured that in this case, it's enough to use some polylog in k number of, so some function not depending on n, but polylogarithmic in k number of colors. This is open. The only bound we have is something just the order of k. But
so this means that the hyperedges at most k.
The hyperedges have cardinality at most k. But with Noga, of course, what you do in mathematics when you can solve a problem, you add it to your assumptions, right? So you add a solution to your assumption or something. But this is somewhat the case, not exactly. What we did is we assumed further that not only that every point belongs to at most k, in fact, you can assume, it's still not trivial, that every disk in the intersection graph has degree k. So every disk intersects at most k other disks. So if a point belongs to at most k disk, obviously every disk intersects, if every disk intersects at most k other disks, it's a stronger assumption because it implies that every point belongs to at most k plus 1 disks, right? If a point belongs to k plus 2 disks, each of those disks intersects k plus 1 others, right? So this is a stronger assumption. But still, it's not trivial to prove a polylog. And even then, we don't know the exact. I conjecture that it's actually log k and not log cube k. So there we needed some geometric insight plus the Lovász local lemma and stuff like that. What else? So again, what if every point belongs to at most k disks? We conjecture that polylog. That would be really interesting because it seems to have deep relation to discrepancy theory and so on. Things like that if you... Again, if you don't follow me now, it's okay because I'm not going to talk about any of this. I'm going to talk about... So, another version of the problem, which I think is interesting, is to... Now the parameter k means that not only that you want every hyperedge to have at least one unique color, you want every hyperedge to have at least k, which is some constant k unique color. So k different elements each have a unique color in that hyperedge. So you want a stronger property. So when k equals 1 is just the regular.
Geometric graph as well? This is also some geometric hypergraph?
Yeah, so this is for the same, like disk, pseudo-disk and stuff like that. Actually anything that... Yeah, no, actually only disk and pseudo-disk, yeah. This also uses some... This actually is true for anything that has what is called linear union complexity. But if it's slightly more than linear, then we cannot make it... no, sorry, what am I talking about? I'm confusing that. Yeah, this is for any... So this k log n could be generalized to other functions, which has to do with the union complexity of the underlying shapes. Yeah, so for this or pseudo-disk, it would be k log n, and this is tight. It's also not a difficult exercise, but still not trivial to prove a lower bound as well, that you can come a construction. There was also a whole industry of online algorithms. What is an online algorithm? So this is a nice question. Let me just mention it. Here's a game, very simple game. We are on the line, and you give me a point. So I play this game against an adversary. The adversary gives me a point. Once he reveals the point, I must assign it a color. And this coloring has to be conflict-free with respect to intervals at any given time. So he gives me a point here. Well, I have to assign it some color 1 I cannot regret later. Now he can always shove a point between any two consecutive points. So now he gives me a point here. So I have to color it with a different color because otherwise this interval will have no unique color. So I color it with 2. Now he gives me a point here. So this forces me to use a new color because I cannot color it with 1 because that interval will not have a unique color, or 2, okay, 3. And so we continue the game. So now actually, the next time he gives me a point, no matter where the point is, I can already reuse the color. Maybe if he gives me the point here, I can use color number 1. Still, any interval has a unique color. And we continue the game, n times. So the question is there a strategy that will assure me to use only log n colors, which is optimal because even in the last moment, in the coloring must use log n colors. But can we do it with log n colors? Open problem. Sounds simple, but maybe not. But so the only deterministic strategy we came up with could assure us a log square n colors. But you can also apply a probabilistic strategy where you can randomly choose your color, and with high probability so the number of colors the total number of colors you would use would be log n times log n or something like that, with high probability. If you weaken the adversary, so there are all kinds of results. Maybe I should skip. Okay, another general result, but it's actually not too difficult. Just generalize does this remind anybody something? This quantity? Right? Any graph with m edges has chromatic number at most this, right? That's a nice exercise. But actually, it's a little bit more than an exercise if you want to conflict-free a hypergraph. It's a nice exercise. If every graph, if the chromatic number of a graph is k, then if you partition the graph. No, I'm not talking about the hypergraph now. You partition the graph into k classes, and you must have at least one edge between any two classes. Otherwise, you could unite these two classes and have a smaller number of colors. So the number of edges you have is at least m. The number of edges is at least k choose 2, right? And k is the chromatic number. So if you do the math, k is at most exactly this. So k is at something like root m, right? But the exact. So they do it for conflict-free colorings of hypergraph with m edges and some more stuff there. Just wanted to mention this. Okay, now we want to talk about the least version, okay? Which is good for any coloring almost you can come up with, not only conflict-free coloring. So the least version would be the following. So not only that you are given a hypergraph, VE, you are given also, the vertices come with lists. Each vertex is assigned some list that you cannot control, but some list, LV. When I say list, I actually mean a set. There is no order. So each vertex comes with some set. You think about it as a restricted colors for that vertex. Okay? So given that, we say that a coloring from V to the union of all the colors in the list is CF coloring from that family of list L if it's both a CF coloring, so it maintains the property, and you also chose for every vertex color from its own list. So the color you choose for a vertex must belong to the list. So this is you can talk about any coloring like that, coloring from lists. So it's a coloring plus every vertex got its color from its list, and we say that H is K choosable, KCF choosable, if no matter what the lists are that are assigned, as long as they have size which is at least K. What is this? What is this? Some bug. Okay. So yeah, K. So as long as the lists all have size K, you can, no matter what the lists are, you can always color the hypergraph conflict-free from those lists. So you don't control the list. The adversary gives you the list. And yeah, so for any family L of lists of size K, H admits a CF coloring from L. And an analog definition would apply to a proper coloring. And we denote the choice number, the CF choice number of H as the minimum K for which H is KCF choosable. I'll give an example. And an analog definition applies for just the chromatic number, the proper coloring of a graph. So it's K choosable if no matter what list of size K, H admits a proper coloring from L. So obviously, if a graph is K choosable, if a hypergraph is KCF choosable, then it's also KCF colorable, because if it's KCF choosable, then assign each vertex the set 1 to K. All the lists are the same. And if you can color from those lists, in particular and this is a CF coloring, in particular you CF color the hypergraph with K colors. So if it's K choosable, definitely you can color with K colors. So the choosability number, so the CF chromatic number is at most the choosability number.
What about the other way?
So the other way is interesting. So we have this inequality. The choice number, so the chromatic number is at most the choice number. If you can do it with k, with list of size k, definitely you can k color it. But the two parameters can be far apart. That's the other one. Even, as some of you might know, for a simple hypergraph, which is just a graph. Okay, so hypergraph of size 2 is just a bipartite graph. Take a complete bipartite graph on 3 vertices on each side. So each hyperedge now is an edge of this bipartite graph. So 2 elements in each hyperedge. So the conflict-free coloring is simply a coloring of that bipartite graph, right? And what's the chromatic number, or the CF chromatic is the same? Yeah. What is the chromatic number of a bipartite? Very good. What is the choice number? So I want to show you that it's not 2, right? To show first easy example where the parameters are far apart. So how do I show you that it's not 2 choosable? I need to give you an example of list of size 2 associated with each of the vertices, such that no matter what color you use, it will not be a proper coloring. So here are the lists. This is the list on one side, and these are the lists on the other side. Okay. So this vertex you can only color from this set, and this vertex you can always only take from this, and so on. So it's a simple analysis, right? I mean, it's a case analysis. Suppose with our laws of generality we choose something for here. I want to show that no matter what we do, it's not going to be a proper column. So suppose we choose 1. The analysis for 2 is the same. So if you choose 1 here, you must choose 2 for here, because it's a complete bipartite graph. So 1 will have an edge here, and this can be colored with 1 or 2, so you must choose 2, right? So you must choose 2 for this guy, and you must choose 3 for that guy, right? But then, this guy cannot have a color assigned to it, because no matter what you choose from him, 2 or 3, there's one conflicting, right? And the same for 2. So you cannot, so the choice number of this graph is not 2, it's bigger. In fact, so I don't remember whose construction is this, but basically those list coloring for graphs, for the special graphs, were initiated sort of independently by Wiesing and by Erdős and who else was there? I don't remember. And this is a simple, and now we can generalize this example of bipartite graph to show that actually the choice number of bipartite graph can grow as large as you want. It's not, maybe it's always 3, it's not 2, but actually for any k, there is a bipartite graph such that, so meaning it's 2 colorable, but the choice number is at least k, is more than k. So I claim that if, so you see in PowerPoint I don't know how to do 2k minus 1 choose k, so I just wrote. Okay, so if n is if you have a bipartite graph with n vertices on each side, and n is 2k minus 1 choose k, so that's the amount of vertices you have here, and this many vertices here, and you take the whole any per an edge. So this graph is not k choosable. Here's the proof. Suppose it is. So let's think about this 2k minus 1 choose k vertices as having ID, which is a k tuple, a subset of size k out of the decay. So each vertex has an ID, and the ID is just a subset of size k out of 2k minus 1. And suppose you could, yeah, so not ID, sorry. You assign each vertex that list. So this vertex gets some k tuple out of a list of a k tuple, and all the k tuples are going to be all the 2k minus 1 choose k. So for the other side. So now suppose, so I claim that you cannot color from those lists. Suppose you can. If you can, let's look at the coloring you use for those vertices. Suppose in total, after you assign the vertices, after you assign the color to the vertices, suppose you use the total of less than k colors. That's impossible. If you use the total of less than k colors, then there is at least, so you use at most k minus 1 colors from some set of 2k minus 1. There are some k colors that have never been used, right? But there is a vertex whose list is exactly these k colors, right? So it means that you haven't chosen a color for that vertex, right? So first of all, it means you use at least k colors. So pick some k colors that you used in the coloring here. Pick some k of them. There is a vertex here that has exactly these k colors, which means that this vertex cannot be assigned any color, because for any color here, there's a neighbor assigned with that color here. Okay? So the graph is not k-choosable. Okay, so it shows you already that this could be far apart. In fact, if you write n equals 2k minus 1 choose k, then the graph, the choice number is at least something like log n over log n or something like that, right? Okay, so first I want to show you a general theorem that says that for any hypergraph, the choice number is at most the chromatic number times ln n, log n, why did I put? Yeah, ln n, okay, ln n plus 1. This is a very simple probabilistic proof. And it's true for any coloring almost you can come up with. So of course it's also true for the proper coloring. So but let me focus on this. So here's the proof. So suppose we have a hypergraph whose chromatic number, the Th chromatic number is k. So I want to show you that the choice number is at most k star, which is k ln n plus 1. So it means that I want to show you that if each vertex has a list of size at least this many, at least k stars colors, then I can always assign a color to each vertex. Each vertex gets some color from the list, such that this coloring will be a conflict-free coloring. Okay, so we know that the chromatic number is k. So let's look at this partition of the vertices into these k classes that are induced by this some coloring, Cf coloring with k colors that exist. Now each vertex comes with a list of some k star colors, and you need to assign one color to that vertex. So what we'll do is before we assign color, we're going to dilute the list a little bit. We're going to dilute the list in such a way that from every list we're going to erase some set of the colors, so we're not going to use them at all, in such a way that the lists are not going to be empty, and in such a way that vertices from different color classes, if you look at the sublist that we got after we diluted the list, they are going to be these joint lists. So if we can do that, so basically what do we want? So we're going to erase some of the colors. Here is the process, the way we erase. But let me before we do it, let me just again repeat what I want to do. So I have this this is some partition of to k, not k star, k colors. There's some vertices here, there's some vertices here. So the meaning that this partition is a conflict-free partition, coloring is a partition, it means that every hyperedge, what is a hyperedge? It's some subset of the vertices, right? This is the subset contains some elements colored. This is a color, this is a color, and so on. But it means that it intersects at least one of the color classes in exactly one point. Right? That's what it means. Now I'm going to dilute the list associated with the point such that all the lists are going to be not empty, and also any list of a point of a vertex here and a list of a vertex in another class are going to be disjoint. If I can do that, I'm done. Because then consider the reduced list. Then just pick any color for the.
So
So I'm gonna, this guy has a list, and this guy has list, everybody has list. I'm gonna delete some of the elements. I'm gonna delete them and get some new list.
There's no edge containing the two vertices. Even if there is no edge containing the two vertices.
You mean that there will be disjoint? Yeah. It's gonna be,
Any two vertices in distinct color classes will have disjoint.
Exactly. That's it.
Regardless of where the edges are.
Yes. And if you can do that, you're done, because just pick a color, not pick a color for each vertex, pick a color from its list, which is not empty, you're done. Why? Because look at any hyperwedge, you know that there's at least one, in one of the color classes you have exactly one vertex. You picked a color here, and why would it be unique? Because you know that no matter what color you picked, it's going to be different from all the colors here, because the list associated with that color is disjoint from all the other lists. Okay? So that's what we need to do. We need to shrink the lists and make them disjoint for different color classes, and that's very simple. Here's the proof. The proof is by the probabilistic method. So you just go over all the colors that appear in the union of all the lists, and for each color you do the following independent random trial. You choose each class with probability 1 over k. Okay, so that's going to be the class that you're not going to erase this color from all the lists. And what you're going to do, so for a color you pick a class, maybe this one. And now, if this color appears in any of the lists in the other classes, just erase it from. So just erase this color from all the lists except from the class you picked with probability 1 over k. That's all you do. Obviously, after you did this process, the lists are going to be disjoint, right? Because a color can survive only in lists in one color class. So the question is, how can you do it such that all the remaining lists, all the lists are going to be non-empty, right? You might have deleted everything. That's not good. So all we need to show now that after you do this, you pick any color. So you go over all the colors, and one by one you assign it with probability 1 over k to one color and just delete it from the other list. So now we have to prove that the lists are still with positive probability going to be all non-empty. Okay? Yeah, so this is the process. So fix one list. Okay? After it's been diluted, call the diluted list. So LV is the original list, LV prime is the list after you erase some of the colors. What is the probability that the new list for a fixed vertex is going to be empty? Very simple. The probability that you take a color in that list, what is the probability that it's going to be empty? It's going to be erased. It's not going to be erased with probability 1 over k. So it's going to be erased with probability 1 minus 1 over k. But you have k star of those. So the probability that all of them will be erased is 1 minus 1 over k to the k star. And 1 minus 6 is at most e to the minus 6. That's a simple inequality, right? So this is at most e to the minus k star over k. And if k star is what's written there, this is less than 1 over n. So just apply the union bound. What is the probability that at least one of the lists is going to be empty? It's at most n times the probability of that, which is less than 1. So it's a positive probability none of the lists are going to be empty. You're done. Right? So questions about that? Okay, so and that's very general. What I did here with del pi also for the regular chromatic number. Not every, but some. There's a bunch of properties that probably maybe has to do with simple logic, that if you have some coloring, you have an upper bound in the chromatic number, the choice version would be at most this time ln n. Okay, now I'm going to talk about special hypergraphs, which even though we know that we can we almost have nothing to answer, right? If we have some bound on some CF chromatic number, then it's at most this chromatic number times ln n for the choice version. But still, it is interesting to look even in this simple example, where we have points and we color them such that any interval contains some unique color. That's the first example I gave yesterday. We call it the interval, the discrete interval hypergraph. So all subsets of consecutive elements are sets in that hypergraph. And just think about the elements as the number 1 to n. So I showed yesterday that the CF chromatic number is log n plus 1. It's at most and at least for, I mean, well, it should be log n floor plus 1, exactly. Let me remind you why this is true. So again, if I'm talking about conflict-free coloring with respect to intervals, so if you color those points, no matter what you did, I'll take an interval containing all the points. There's some unique color there. I'll take a large interval containing at least n minus 1 over 2 of the points. I have another unique color which cannot be the first unique color that I found because the unique color was global. So 2 is the only color that appears in that interval. So then I have a sub-interval which contains at least n over 4 and so on. And I find a new color and so on. So you find at least log n colors, a lower bound. So and this lower bound holds for points, as I mentioned, with respect to unit disks, because any interval, if you put the points close enough, any interval could be realized as some intersection of the line with that disk. That's easy to see. So now, we also show that the CF chromatic number is easy to see, that it's at most log n plus 1. You color the median point with 1, and then you recurse on right and left side reusing colors, but keeping them distinct from 1, right? And we have this separation, nice separation property, basically, that if you have some hyperedge containing elements from the right and from the left, it will also contain this uniquely colored element. So this separation, so by the adapter and right, the choice number of such a hypergraph is at most log n times ln n, which is log square n, right? But then we can actually show that it's the same. It's actually log n plus 1. So if you look at this argument of the separation, I claim that if you have lists of size log n plus 1 in each of the vertices, you can still color from those lists, no matter what they are, as CF coloring. And the proof would be the same. You pick a point, which is the median, and you look at the list associated with that point. It has log n plus 1 element, colors, and you need to pick one. Just pick anyone, doesn't matter. Pick some color, and erase that color from all the other lists. So remove that color you use from all the other lists. All the other lists had size log n plus 1. Now they all have size log n, and you recurse on this, arguing about the size of the list on the left and right. That's going to work. But, so keep in mind that one could talk about, so this is like a permutation that we take intervals. Now we can talk about two permutations. So now we have the same n elements. They appear in some order here and some order here, and I want to conflict-free color the points such that any interval here or here is going to have a unique color. This used the property, in the one-dimensional case, it used the property that if you have a point, that's it. This is separation, you can color it uniquely. No element, no hyperedge containing points from here and here will avoid this point. But now, this is not true anymore. If you pick the median point in the second permutation and the median point in the two permutation, this is not a separation. There can still be an interval here that contains point from here and here without containing this point or this point. So these two guys, actually you can have an expander if you know what I mean. I don't want to get into it. You can have an expander realized by two permutations. So there's no so small separation. Or you can just think of a grid which is two permutation. The grid, the root n by root n grid has root n, and it separates, so we'd have at least root n, but it's two permutation. But just an observation, because we're going to use these families of permutations to solve some geometric problem. How much time do I have? Nothing.
15 more minutes.
15. Okay. So let's go to the next sort of easy case. So I showed you how the choice number of points with respect to intervals is the same as basically as the chromatic number. It's log n plus 1. What about, yes, you want to?
So this two permutations, is that the same as the axis parallel box?
No box. No? Strips. Axis parallel strips. Okay. Let's try to do generalized intervals to the next step, which would be points in the plane with respect to half planes. So you have a bunch of points in the plane. CF color, we mean assigning color now that every half plane would contain, so any half plane, you take a line, you look at all sets of points on one side. This is a hyper edge. You want a unique color. It's easy to see that log n colors are enough because it's almost the interval case. Why? +1. So basically what you do for the regular coloring, you just ignore you take the convex half of the point, you ignore the internal points. I mean, you can use one color that you will never use again for the internal points, and then the half points are almost like intervals, just like cyclic intervals. So you can reduce it to intervals. It's the same. So plus one more color for the, so any hyperplane that contains some points must also contain exterior points, and if one of the exterior points has a unique color, definitely it's going to be also unique because the interior points got different color. But for the choice version, it's already you see the difficulty. So for the choice version, the problem is it's almost identical to the discrete case, but for if the points are in convex position, it's really a plus effect from a constant addition constant of 1. It's the same. It's just that in order to separate, you need 2 points. So you need 2 points. You pick a color for each of them, distinct colors, and then erase these 2 colors from all the other lists. As long as all the other lists are going to be, you're going to use just the one-dimensional analysis. That's good. That's not a problem. But if you have interior points, you can say, well, let's just choose a color for each of the interior points and remove this color from all the list of the exterior points, right? But the thing is that it might be that all the lists associated with these interior points are disjoint, and you get many colors here if you pick some color. I mean, you cannot pick, whatever color you pick for each of the points, it's going to be distinct, all distinct. It's going to be like, suppose you have n/2 points here and n/2 in the exterior, and all the colors you would use for this n/2 is going to be distinct n/2 colors, but all those lists here have are going to be the same list, and it's exactly this n/2 colors that you used. So you might erase too much. You want to erase only a constant number from those lists and say, oh, okay, now the lists are still big and we can do the one-dimensional, right? So basically, what do we want? We want, that's what I said, we want the following property. So let's call P1 the extreme points, the half point, the red points, and P2 the interior points. And let's look at the set of lists associated with the points. So we want to dilute the list in such a way, as before, in such a way that the interior lists are going to be disjoint from the exterior list, but they are going to be non-empty. And in addition, we want also the exterior list to still have size log n plus 1 or something like that. Because we need. So we want this. Okay? We want to erase some colors from each of the lists in such a way that the new lists, okay, are going to be all, first of all, not only the exterior lists are going to be big, they are going to be of size log n plus 1, and the interior list, I just want them to be non-empty, okay, and I want to be each interior list disjoint from each exterior list. If we do it, we are done, because then we can just apply the one-dimensional assignment of colors for the exterior list and any color from the interior list. So this, the same thing, you do, the proof of this existence is again probabilistic. You just pick any color and either erase it from all the interior lists or erase it from all the exterior lists and continue over all the colors. And now you need to use a little bit more sophisticated, you need to use Chernoff bound in order to show that, say, if all the exterior lists was originally had size 10 log n, after this process with constant probability, all the lists are going to have size at least log n plus 1. Because in order to erase too many, you have to deviate from the average by too much, and by Chernoff bound, it's going to be only small probability, and you can multiply by 1. Okay? So this trick is easy here. How about points with respect to unities? These become more difficult. So we claim that still we can do log n. This is a more general case than half planes, because because unit disks are almost half-planes, but not exactly. Okay, so unit disks, so each half-plane could be thought of as a big disk, but so if you have a bunch of points in the plane, this is a unit disk, and you have a bunch of points, all kinds of points. If you fix a small piece of the plane, a square, and look at the points here, then if you look at the unit disk, it looks huge compared to those points, something like that. It's going to behave almost like a half-plane, but not really. It's going to behave like a half-plane only, for example, if you restrict all the unit disks to sort of contain this point or something like that. So you take a bigger square, and you have these 4 points, and you can make it in such a way that any unit disk that intersects the little square will either contain that point or that some point, maybe 2, but at least 1. And if you look at all unit disks containing that point, the way they behave here is like half-planes. But the thing is that, okay, so they behave like half-planes. So the analog of interior and exterior, and the exterior has some linear ordering that we use. But some points here could have some linear orderings. Some exterior points with respect to those disks going to have linear ordering that is induced by this direction, but the same points could appear in a different linear ordering by disks that contains this point that come from here. Okay, it's going to be different permutation, and so here and here. So now we have basically 4 linear, something like. So I need to quickly say that there is some reduction. So we first partition the plane into some grid cells of constant, and the grid cells are partitioned into classes, a constant number, in such a way that 2 grid cells that belongs to the same class, they are independent in the sense there is no unit disk, they are too far apart. There is no unit disk containing a point both from here or from here, because there is no unit disk that can intersect these 2 guys. So there is a constant number of classes, but in using the probabilistic method, if the list associated with the points were big, then we dilute them a little bit, and now lists from different classes are going to have disjoint list. So for example, if this is a different class, all these guys that might conflict with this, then all the lists here are going to be pairwise lists. Any point here and any point here is going to have pairwise disjoint list. So we need to focus on one grid cell. And one grid cell is going to look like this, something like that. I'm just, and so this whole introduction here was to say that the real problem arises from the fact that, so you can there are 4 types of disks, and a disk could belong to more than one type. But each disk contains either some point here or point here and so on. So there are 4 types, and there are the notion of extreme points according to the type. So a point could be one extreme if there is a disk that comes from here and contains only that point from this grid cell. So it will be one extreme. It could be 2 extremes, 3, it could be a subset. And those extreme points, and we can also ignore those that are not extreme in any. And some extreme points are going to be in linear ordering. But we have four possible linear orderings. So I'm going to skip the exact calculation, and I want to show. Actually, this was the main part of the talk, which I'm not going to have, is to show you that actually, if we solve this more general problem, then we solve the unit disk problem. Here's the more abstract combinatoric general problem. We have a family of R permutations on the same set of n elements. Okay? In our case, the R was 4. So we find the hypergraph to be just the analog of the discrete interval hypergraph. Is just that now you allow intervals in any of the permutations. So you have, so the n elements of the vertices, E is the set of all intervals in all the permutations, meaning exactly this. So you look at all possible, so in the ith permutation you look at all possible intervals pi of S to pi r of some t. And you look, and the interval could be in any of the permutation. If there's only one permutation, it's easy. This because the choice number is log n plus 1, but now we have more than 1, and we don't have this separation property. So, how much time do I have? 5 more. Okay, I just really quickly should try to build. So here's the theorem. There is a constant that depends only on this dimension. I call dimension the number of permutations. So it depends only on the number of permutations R, such that the choice number of that hypergraph is at most C log n. Okay? And here's the proof. So we need the following lemma. There exist two constants that only depend on R, which is D and C, and two functions f and p that both you can think of as a coloring of the elements, such that small intervals, so our hypergraph consists of permutations. We have R of those permutations. This permutation is pi 1, pi R, right? And we have intervals in all permutations. Those are subsets of the same n elements. And so we can partition, we have these two partitions, f and p, such that all the small intervals, if you pick a permutation and the interval is not too big, it has only a few elements, and by few I mean some, they will have different colors in terms of f, different f values. Okay? So it means that the values of any interval of the form pi I s and so on, the f values are going to be all distinct. Polychromatic. It's going to have distinct colors in terms of f. And by small and big, I mean actually d. So the intervals that have less than d elements. Sorry, C. C. All the intervals that have at most C elements. Okay, this is one property. The second property, that if the intervals are not small, they are big, they have more than C elements, then if you look, for example, for any permutation, fix a permutation I, then if the interval is big, then there is at least one element colored with I in the other function P. Okay? I'll show a picture. Here's the picture. So let me go first to the picture and then go back here. So this is the so here I denoted elements. This is the I permutation. I denote, and there's some permutation. I painted red, marked red those elements that P, the function P, gave exactly the value I. The value P is between 1 to R. And those are the other ones. And all I claimed is that small intervals, okay, they have they're going to have all distinct colors. This is going to be coloring, but all distinct colors in terms of the other coloring. Big intervals are going to have at least one element which is colored under P by I.
So
the idea is each element has two colors. You can think of it as just a constant number of colors. It's the Cartesian product now. But if you have a constant number of colors, what we can do is dilute the list in such a way that lists in different colors are going to be disjoint. Okay? And now, if we did that, we can regard independently each permutation as a one-dimensional case and just apply the one-dimensional analysis, but only on the red points. So ignore those points. Just take the median point among the red points, choose the color, delete it from the other, this and so on. Okay? Why is that good? Why is that a valid conflict-free coloring? Because we made sure that small intervals that may not contain red points but still contain something, they have disjoint lists. So of course it's going to be a conflict-free coloring with respect to those intervals. Big intervals, they contain at least one red point, right? And we're going to use the red points in such a way that among the red points there's going to be a unique color. This color also should be different from all the colors given for the other elements, but they have this disjoint list from the red ones. So it's going to be okay. That's more or less the sketch of the proof. So maybe I should... I can prove the lemma, so I won't have time to prove the lemma. It's nice. It uses... The first function P uses the Levas local lemma, and the second one is some graph argument, and maybe I should stop here. Something like that, right? Okay, and this is the open program. What about arbitrary disk, not unidisc? This is open. All we know is log n squared. So yeah.